You've heard the term GPU, graphics processing unit, thrown around a lot. Originally, GPUs were all about making video games look amazing, handling complex visuals your CPU just couldn't manage. It's the dedicated hardware in your computer, console, or phone that brings digital worlds to life. But today, GPUs are much more than just graphics cards. They're now powering breakthroughs in AI, scientific research, and even blockchain technology. Why? Because their unique design makes them incredibly good at handling massive, repetitive tasks all at once. While your CPU is a generalist, great at doing lots of different things one after another, the GPU is a specialist, built to process huge amounts of data in parallel. That's why it's essential for everything from smooth gaming to training AI models. Understanding GPUs means understanding the engine behind much of our digital future. Whether you're a gamer, a creator, or just tech curious, the GPU is at the center of it all. So let's dive into how this powerhouse works, and why it's become so much more than just a graphics card. Let's break down the difference between a CPU and a GPU. Think of the CPU as the manager's smart, versatile handling complex tasks one at a time. The GPU? It's an army of interns each doing simple, repetitive work, but all at once. For tasks like stuffing thousands of envelopes or rendering millions of pixels, the GPU's parallel approach wins. CPUs have a few powerful cores for quick sequential jobs. GPUs have thousands of smaller cores for massive, simultaneous workloads. The CPU is optimized for low latency, instant responses. The GPU is built for high throughput, sheer volume. They're not competitors, they're teammates. The CPU runs the logic and hands off the heavy lifting to the GPU. The GPU's thousands of cores paint the picture pixel by pixel, all at once. One is a scalpel, the other a paintbrush. You need both to create digital masterpieces. The GPU's real superpower? Parallel processing. Imagine painting a giant wall. The CPU is one person with a brush, precise but slow. The GPU is 1,000 painters, each tackling a section at the same time. That's how GPUs handle graphics, breaking a huge problem into thousands of tiny, identical tasks. Each core calculates the color, lighting, and texture for its assigned pixels. This embarrassingly parallel approach is perfect for rendering high-res images and video. As screens get bigger and games get more detailed, GPUs just add more cores to keep up. That's why modern GPUs are in an arms race. More cores mean more power for ever-demanding visuals. Parallel processing isn't just efficient. It's essential for today's digital experiences. And it's the reason GPUs have become so powerful. So how does a GPU turn 3D models into stunning visuals? It's all about the graphics pipeline. The CPU tells the GPU what to draw geometry made of triangles. Vertex shaders process these points, mapping them in 3D space. The GPU connects them into a wireframe, then rasterizes it, turning 3D shapes into a 2D grid of pixels. Pixel shaders then calculate the final color for every pixel, lighting, shadows, textures, reflections. This is where realism comes alive. Advanced shaders and effects like ray tracing simulate real-world lighting, creating lifelike images. Ray tracing traces the path of light for ultra-realistic reflections and shadows, but it's computationally intense. Modern GPUs have dedicated hardware like RT cores to handle these demanding tasks. The result? Games and visuals that blur the line between digital and reality. GPUs aren't just for gaming anymore. Around the mid-2000s, researchers realized GPUs could accelerate all kinds of parallel tasks, not just graphics. Scientific research, like simulating protein folding or weather patterns, sped up dramatically with GPUs. Cryptocurrency mining took off because solving cryptographic puzzles is highly parallel, perfect for GPUs. This led to massive demand and even shortages. But the biggest shift? Artificial intelligence. Training deep learning models requires huge amounts of repetitive math, matrix multiplications, across massive datasets. GPUs made this possible, unlocking breakthroughs in AI that CPUs alone couldn't handle. The GPU's parallel architecture is now the backbone of the AI revolution. Let's peek inside a GPU and see what makes it tick. The core count, CUDA cores for NVIDIA, stream processors for AMD, shows how many parallel tasks it can handle. Top GPUs have tens of thousands of these tiny processors. VRAM, or video RAM, is the GPU's ultra-fast workspace, storing textures, models, and the frame buffer. More VRAM means smoother performance, especially at high resolutions. Clock speed measures how fast each core works. Higher speeds mean faster calculations. It's a balance. More cores for parallelism, higher clock speed for quick results. Modern GPUs also have specialized hardware, RT cores for ray tracing, tensor cores for AI, and deep learning. These dedicated units handle specific tasks more efficiently than general-purpose cores. Overclocked cards push performance even further. Today's GPUs are complex, multi-talented chips, each part optimized for a different job. It's all about using the right tool for the right task. Today, GPUs are the engines behind the AI revolution. Training massive AI models now drives GPU innovation as much as gaming does. High-end GPUs are designed for both stunning graphics and advanced AI workloads. NVIDIA's CUDA platform was a game-changer, letting developers tap into GPU power for non-graphics tasks. CUDA made programming GPUs for AI and science accessible, sparking a software ecosystem. Deep learning breakthroughs, from image recognition to language models, were all trained on GPU clusters. Training these models means running trillions of calculations, impossible for CPUs alone. GPUs, with their parallel architecture and specialized cores, made the impossible possible. Now the race for better AI is a race for better GPUs. The future of medicine, autonomous vehicles, and creative tools all depend on GPU evolution. From rendering fantasy worlds to building our digital reality, GPUs are at the heart of it all.